Okay, hello, my name is Tahsin, his name is Bilal, and today we're going to be talking about dual axis solar panel tracker. Move on.
So first we have our challenges that we face. So the challenges that we face that because solar panels are static in nature, when they're normally still they lose about 35 to 45% of the sun rays that it collects. So because of this huge loss, the energy that has a potential to be gained has been lost very much, and also the static angle losses.
Now, the solar tracker prototype, dual solar panel assembly, high efficiency modular photocells. These photocells are over here. They're used to detect where the sun is and help the solar panel know where the sun is so it can efficiently track it. Tilting support mechanism that helps it with the dual axis rotation, helps it rotate 180 degrees.
So here we can see we have built a 4-quadrant mechanism with 4 LDR sensors in each quadrant. So because LDR sensors are not able to detect every single lighting, when you keep it in sunlight just barely 2 centimeters apart, they all will get about the same reading. So that's why we have used a long 4-quadrant system. So when the shadow comes, due to the quadrant system, for example, we have the sun here. This wall and these quadrants cause shadow in these. So rather than all having the same sensitivity, they all, due to the shadow, the sensitivity reduces, and due to this, the robot detects that the shadow is facing this way, and hence the sun is also coming from that way.
And now our design has like, let's say, a high contact area that helps it with wind resistance, hence harsh environments like, let's say, Mars or bad weather on Earth with high wind, not rain. So just point that out because rain won't work because there's no sun. Low center of gravity, as mentioned before, it has a heavy base and it helps it with wind resistance and space efficiency. It's very compact, it's very small because our design philosophy is the less is more.
Next, we come to the hardware part. So for hardware, we use an Arduino Uno, and rather than servo motors, we use stepper motors. The reason we use stepper motors is because its acceleration deceleration makes it very stable and smooth, and also it has a lot more torque. And the 4-quadrant system we also use just using 4 LDR sensors, and the last one was the 3D frame.
Okay, now for our engineering innovations, we have passive balance control. It utilizes the tilting motors to gain more, let's say, sun power.
Next is the future planning. So we're planning to integrate it and AI. So rather than it having to do a real-time calculation and waste more energy, it can take about maybe past 2-3 days info and then make prediction based on it. So in the future, rather than taking real-time measurements and doing real-time tracking, it can just use the previous predictions and use the AI to do movements.
This is where we think this will be very useful. Planetary exploration outpost. This is where we, let's say, have limited resources. We need to use the sun, we need to utilize, and that's where, let's say, the low power draw comes in play, the low space, because it's easier to transport. You can put it into, let's say, storage components, you can take it apart. It's much more mobile. And desert solar panel farms. This is where, let's say, the harsher environments come into play, and where our lower center of mass and higher contact area helps us a lot with keeping it in place and making sure it does its job more effectively. And for future implementations for this area specifically, we might want to add, let's say, some way to clean itself, because the dust, specifically in like desert areas, dust will affect the performance of the solar panels. So if we find a way, and there is a way to clean itself, think of it as like windshield wipers.
So here it doesn't detect the room light and very less ambient light. So here we have got a torch. So as you can see, when we point the torch from downwards, it already automatically tilts. And for example, we point it directly upwards, it will automatically tilt itself towards the top, and even in the left and right, like that. And here is one video for our real life.
Alright guys, so today we're gonna be testing our like 180 rotation solar panel, and as you can see it's starting to do its thing and like it's rotating counterclockwise, surprisingly. Over there, that's the sun. That's why it's rotating this way. And like guys, if you like look closer, you realize how accurate it is. It's like actually going towards the sun. And then it's gonna stop because the sun. Alright guys.
And that's it. Thank you.